Hi, so this is part 3 of the Maxwell stress tensor, and I'll be showing you how to get these certain elements of this 3 by 3 matrix for the Maxwell stress tensor. Okay, so start for the first term. So actually, this is pretty symmetric. That's what's so helpful to remember the Maxwell stress tensor. So last time we derived that we proved the Maxwell stress tensor. Okay, so say that Txx, okay, so Txx is epsilon sub naught of E x, since I equals j, Ex squared of minus 1/2 of Tx, or of the Dirac delta function of xx, which if you recall from the Kronecker delta, that this equals 1 if I equals j, but equals 0 if I does not equal j. So we have minus 1/2 of the magnitude squared of the electric field, which is Ex squared plus Ey squared plus Ez squared. Z squared. Okay. Yeah. Okay. So similarly with the magnetic field, we have the exact same of 1 over mu naught of Bx squared minus 1/2 of Bx squared plus By squared plus Bz squared. Okay. So the diagonals tend to be a little bit messy because you're dealing with more terms. So actually the diagonals are the actual pressure, and the x, y, x, z, and the off terms are more of the shearing if you take in linear algebra. It's more like a linear transformation. So it's like if you take a point and you shear it like that, if you flatten it out. So after simplifying this, we get Txx equals to epsilon naught over 2 Ex squared minus Ey squared. Ex, note that Ex is x component, Ey is y component, etc. minus Ez squared plus 1 over 2 mu naught, factoring out the 2, gives us Bx squared minus By squared minus Bz squared. Okay. So we could do that for any of the terms on the diagonal, Ty, Tz, etc. We can also find eigenvalues of the Maxwell stress tensor, which is going to be a little bit, which I'm not going to do in this video, but if you're interested, that lambda equals the determinant of your Maxwell stress tensor minus I times lambda equals 0, not lambda, where lambda is an eigenvalue. And lambda could be either real or complex. Okay. All right. And I is the identity matrix. In this case, we're dealing with a 3 by 3, so it's 1, 0, 0, 1, 0, 0, 0, 1. That's I. Okay, so it's a little bit of an application. So now, what's Txy? Txy is Txy, so the Dirac delta function is 0, because I does not equal j. So we get epsilon sub naught of Ex Ey plus 1 over mu naught of Bx By. Okay. So we can make this more general. So we can actually now find it. You can do the same for any of the other of the elements. For if you just txty is just an example. So now I'm going to write the general Maxwell stress tensor. It's this big matrix. Really big matrix. Okay, so we found txx, which is pretty long. So I'm gonna try to zoom this in so you guys can see. So we have epsilon sub naught over 2 of ex squared minus ey squared minus ez squared 1 over 2 mu naught px squared minus by squared c squared. So I'm going to separate the elements by a semicolon because it can be very ambiguous. Okay. So now for the txy, we have epsilon sub naught ex ey plus 1 over mu naught of, I'm not going to have enough room. That's how messy it is. So how about this? I'll just do it for other terms. Just show it for txz, because this is a really long matrix to see with the first term. So yeah, it's a long term. So txz is equal to epsilon sub naught of ex times ez plus 1 over mu naught of bx bz. Now, okay. So that's really about it. I'll take a screenshot on what the total Maxwell stress tensor is on my whiteboard. It's just too much and too long just to write everything down. So, yeah. And that's it. Alright, thanks for watching. Remember to like, share, subscribe, and comment. And thank you for watching.